Representation Theory of Finite Groups, Lecture 12, Problem Session number 2. In this problem session, we will try to solve a number of problems related to the second quarter of this course. Let us start with the following problem 1. Determine the character table of the semidihedral group SD16 of order 16, which is given by the following presentation. SD16 is generated by two elements a and x, and the relations are a to the power 8 is equal to x squared and is equal to the identity, and xax is equal to a to the power 3. So note that already in the formulation of the problem, we know that this group has order 16, so it has 16 elements. So let us try to figure out what these elements are. So first of all, x squared is equal to e, so x is equal to x inverse. So the last relation is really that if you conjugate a by x, then you get a cubed. So in particular, we can rewrite it as xa is equal to a cubed times x, and hence any element of this group can be written in the form a to some power I and x to some power j, where I is a positive integer between 0 and 7, and j is either 0 or 1. So if we have a word in x and I, we can use this commutativity relation to reduce it only to the form a to the power I, x to the power j. And since we know that the group has 16 elements, and there are exactly 16 words of this form, so these should be all elements of the group, and they all are different. So this group consists of the identity elements, and then the 7 non-trivial powers of a, and then of x, and a to some power I times x. Without the knowledge that this group has 16 elements, what we just discussed shows that it has at most 16 elements. And to prove that it has 16 elements is quite a non-trivial task. It requires some non-trivial arguments, which we leave for the group theory. And let us focus on the representation theory of this group. So as we know, representation theory of a finite group is combinatorially controlled by the conjugacy classes. So let's start with determining the conjugacy classes of this group. Of course, the first class consists of the identity element. To determine the second class, let us start with a, and if you conjugate a by x, we get a to the power 3. So if you conjugate by x again, we go back, and a commute. So a and a cube should be the second conjugacy class. Now, similarly, if we start from a square and conjugate by x, we get a to the power 6, and similarly, this should be a new conjugacy class. And in the same manner, a to the power 5 and a to the power 7 forms a conjugacy class, and also a to the power 4 is a conjugacy class on its own. Now let's look at the elements which contain x. So if we start with x and conjugate by a, we will get a to the power 7 xa, because a to the power 7 is the inverse of a, and we can reduce it to a squared x using our commutativity relations. So a squared x is conjugated to x. Then if we conjugate by x again, we get xa squared, which is a to the power 6x. And similarly, conjugating a to the power 2x by a, we get a to the power 7 times a to the power 2xa, which is equal to a to the power 7 plus 2 plus 3 times x, which is a to the power 4x, because 7 plus 2 plus 3 is equal to 12, but a to the power 8 is the identity, so this reduces to a to the power 4. So this gives us our sixth conjugacy class, which consists of x, a squared x, a to the power 4x, and a to the power 6x. And the final conjugacy class contains all the other elements. So the first element which is not yet listed is ax. So if we conjugate it by x, we get xa, which is a to the power 3x. Then we conjugate this by a, we get a to the power 7, times a to the power 3xa, which reduces to a to the power 5x, and then conjugating by x again gives x a to the power 5, which is a to the power 15x, which reduces to a to the power 7x. Again, because a to the power 8 is the identity. This gives us exactly 7 different conjugacy classes. This should be C7. So in particular, our general theory says that this group has 7 simple modules. So let's denote the simple modules by Vi, where I is an index from 1 to 7. And let's order them so that the dimension di of Vi increases with the index. So d1 is the smallest module, then d2, and so on, d7. Again, from the general theory, we know that the sum of the squares of the dimensions of all simple modules is equal to the cardinality of the group. So d1 square plus d2 square plus and so on is equal to 16. It is very easy to check that this equation has a unique solution. So d1, d2, d3, and d4 should be equal to 1, and d5, d6, and d7 should be equal to 2. So this is just a straightforward verification. So in particular, we have 4 one-dimensional modules and 3 two-dimensional modules. So let us first think about the 4 one-dimensional modules. So V1, V2, V3, and V4 are 4 one-dimensional modules, and they all are isomorphic to C as a vector space. But these are non-isomorphic modules, so the action of our group on them should be different. So we can take V1 to be the trivial module. So such module always exists, so both generators A and X act on it as the identity. For the module V2, we take the sign module, and this is a module on which both A and X act as -1. So this is a module structure follows from our presentation. So if we plug in here -1 for A and -1 for X, then here we get -1 to the power 8, which is 1, -1 to the power 2, which is 1, and here we will get -1 -1 -1 is equal to -1 to the power 3. So the defining relations are satisfied, so this gives us our module. Similarly, as the third one-dimensional module, we can take the module on which A acts as 1 and X acts as -1. Again, plugging this into the defining relations, we see that they all are satisfied, and so this gives us a module structure. And finally, as the fourth module, we take the one where A acts as -1 and X acts as 1. So in all these cases, by checking the defining relations, we convince ourselves that these 4 different structures really give us modules over our group. So we know everything about the one-dimensional modules. Now we need to think about how to construct two-dimensional modules. This is now a good time to note that our group SD16 has a non-trivial center. So center is just the union of all singleton conjugacy classes, and we had 2. So we had a conjugacy class of the identities, always exists, but we also noted that a to the power 4 was a singleton conjugacy class. So this means that a to the power 4 belongs to the center, and in our case, the center just is equal to the identity and a to the power 4. So if we take the quotient by the center, we force a to the power 4 to be the identity. So we get the group with the presentation a, x, the generators, and then a to the power 4 is equal to x to the power 2 is equal to the identity, and xax is equal to a to the power 3. And this is a classical presentation of the dihedral group d2 times 4. So this means that d2 times 4 is a quotient of SD16. So in particular, any representation of d2 times 4 is a representation of SD16 via this quotient map. So we can take the defining two-dimensional d2 times 4 module and consider it as a module over SD16. And since this module is simple over d2 times 4, Of course, it's also simple over SD16. So we say that this is our module V5, and in this way we construct a two-dimensional SD16 module. One can also note that all our 4 one-dimensional modules also come from this construction. They are lifts of the 4 one-dimensional D2 times 4 modules. We have already computed previously the character table for D2 times 4, and we can use it to write down the character table for the modules V1, V2, V3, V4, and V5 for our group SD16. So in particular, we see that the center is the union of the conjugacy classes C1 and C5. So for these two conjugacy classes, the characters, of course, coincide, because on all these modules, the identity and a to the power 4 act as the same linear transformation. And then, so the trivial module has a trivial character, all ones. So V2 has -1 at the places where we have a and x, and then we have to figure out what are the values of the other elements. Similarly, V3 is defined so that a acts as 1 and x acts as -1, and then we have to figure out the rest. And V4 is given by a acting as -1 and x acting as 1, and we have to figure out the rest. And for the two-dimensional module, we can just take the character for the D2 times 4 module and lift it to compute the character of SD16 module, which we get using this projection. So the value on C1 and C5 should be the same. The value at C3 will be -2, and the rest is 0. Okay, we have successfully constructed one simple two-dimensional SD16 module. We need 2 more. In order to construct them, we will use induction. Consider the subgroup H of SD16, which consists of all powers of A. It is a cyclic group of order 8, and it has index 2 in SD16. We know that simple representations of cyclic groups are determined by roots of unity. So let us fix a primitive 8th roots of unity, which we denote by zeta, and we take for it the complex number 1 plus I divided by the root of 2. Then we have the one-dimensional H module n, on which the generator A acts via this zeta. So we can take this one-dimensional module n and induce it up to the whole group. Since H has index 2 in SD16, the outcome will be a two-dimensional SD16 module. So induction from H to SD16 of n. We also know that the original module n is an H submodule of this induced module. So in particular, it follows that our primitive 8th root of unity zeta is an eigenvalue of A on the induced module. We know that this eigenvalue does not appear in any of the simple modules V1, V2, V3, V4, V5, which we constructed before. In particular, it follows that the induced module must have a simple summand which is different from V1, V2, V3, V4, and V5. But we know that any remaining simple summand has dimension 2. And since the induced module has dimension 2, we deduce that it is simple, and so we can take as V6 this induced module. So the action of the generators A and X on the induced module is given by the following matrices. A acts by the diagonal matrix which has zeta and zeta to the power 3 on the diagonal, and X acts as the matrix 0, 1, 1, 0. So it swaps the two basis elements of the module. And this can be computed directly from the definition of the induced module. So using these two matrices, we can compute the matrices which represent the action of all other elements. And here we compute the matrices which represent the action of one representative from each conjugacy class. So A square acts as a diagonal matrix with I and minus I on the diagonal. A to the power 4 acts as minus 1. A to the power 5 acts as a diagonal matrix with minus zeta and minus zeta cubed. XA acts as the matrix 0, zeta cube, zeta 0. And now we can use these representatives to write down the character table of our module V6. So it has dimension 2, so the identity acts as the identity matrix, its trace is 2. So C2 contains A, so its trace is zeta plus zeta to the power 3, but zeta is 1 plus I divided by root of 2, and zeta to the power 3 then will be minus 1 plus I divided by the root of 2, so their sum will be root of 2 times I. The class C3 contains A square, and the trace of the matrix with I and minus I on the diagonal is 0. C4 contains A to the power 5, so here we have minus zeta and minus zeta cubed, so the trace is minus z of C2, minus root of 2 times E. C5 contains A to the power 4, the trace is minus 2, and C6 contains X, the trace is 0, C7 contains XA, the trace is again 0. So we need one more module, and we know how to get simple modules. If you take any simple module and tensor it with a one-dimensional module, you will always get a simple module. And then, if we take the one-dimensional module V2 and tensor it with the simple module V6, we have just determined the character of V6. We know the character of V2. We multiply the characters, and so we can read off the character of the simple module V2 tensor V6. And we see that the outcome differs from all other simple characters. So this means that this should be a new simple module. So we take as the last simple module V2 tensor V6. And we can now write down our answer. So for the first 5 modules, we had the answer kind of written off from the dihedral group D2 times 4, and V6 and V7 were computed separately. So this solves the first problem. Problem 2. Prove using representation theory that SD16 is not isomorphic to the dihedral group D2 times 8. So we have just analyzed the representation theory of SD16. In particular, we computed the simple modules and their characters. So what we will do, we will similarly try to analyze, but in a more concise version, the representation theory of D2 times 8 and show the differences, thus proving that it cannot be isomorphic to SD16. Recall that D2 times 8 has the following presentation. It is generated by the rotation of order 8 and by the reflection S of order 2, and the relation between them is that SRS is equal to R to the power 7. So here R is a counterclockwise rotation by 45 degrees in R2, and S is the reflection with respect to the horizontal coordinate axis in R2. And the difference between SD16 and D2 times 8 is that in SD16 we had the relation XAX is equal to A to the power 3, while in D2 times 8 we have SRS is equal to R to the power 7. So we will try to compute at least some part of the character table of D2 times 8 and show that it is significantly different from the character table of SD16, which we have just computed. In the dihedral group D2 times 8, the force power of the rotation is a rotation by pi in R2. And the matrix of this rotation is just the negative of the identity matrix. So in particular, this rotation is given by a scalar matrix, so it is a central element. So the subgroup consisting of the identity and R to the power 4 is just a central subgroup. In particular, it's a normal subgroup of D2 times 8. And the quotient of d2 times 8 by this subgroup, which we denote by k, is again isomorphic to d2 times 4. This is very similar as for the group SD16. So in particular, any simple d2 times 4 module is a simple d2 times 8 module via this map. And we know the character table of d2 times 4, so we can write down the corresponding part of the character table of d2 times 8. And in particular, d2 times 4 has 4 one-dimensional simples, the trivial module, the sign module, and 2 mixed sign modules, and it has 1 two-dimensional simple. This is a defining representation of d2 times 4. And the important thing for us is that all entries of the character table of d2 times 4 are real numbers. So the corresponding piece of the character table of d2 times 8 will consist only of real numbers. So similarly to the previous problem, consider the subgroup H of d2 times 8, which consists of all powers of the rotation R. Again, this is a cyclic group of order 8, and it has index 2 in d2 times 8. So we take the same primitive 8th root of unity zeta as we had in the previous problem, and we can consider two one-dimensional H modules. The module n, on which the generator R acts as zeta, and the module k, on which the generator R acts as zeta to the power 3. So we take these two different one-dimensional H modules, and we induce them up to d2 times 8. So then we take these induced modules and we compute the action of the rotation and of the reflection S on the induced module V. So this is the induction of n from H to d2 times 8. And this is given by the following matrices. The matrix of R is a diagonal matrix with zeta and zeta to the power 7. And the matrix of S is 0, 1, 1, 0. And now we see the difference with SD16. So this position, zeta to the power 7. So this is because the conjugation of R by S is R to the power 7. In SD16, we had the conjugation of A by X was A to the power 3. So we had here zeta to the power 3. So this is the difference. And the matrix of S is the same as the matrix of X in the previous problem. And similarly, on the second induced modules, the matrix of R will be the diagonal matrix with zeta to the power 3 and zeta to the power 5 on the diagonal. And the matrix of S is 0, 1, 1, 0. So S just swaps the two basis elements. And in both cases, the two matrices have no common eigenvectors. So the diagonal matrix means that it's only the basis elements which are the eigenvectors, because we have different elements on the diagonal. And the second matrix has eigenvectors 1, -1, and 1, 1. So in particular, we have a two-dimensional module, no common eigenvectors, which means no one-dimensional submodules. So both of these induced modules are simple. So the value of the character of the first module V at R is just the sum of the diagonal entries, so it's zeta plus zeta to the power 7. But this is now the root of 2. There is no I here, because 1 plus I divided by root of 2, and zeta to the power 7 is 1 minus I divided by the root of 2. If we add them up, we get root of 2. And the evaluation of the character of W at R is the sum of zeta to the power 3 and zeta to the power 5, which is minus root of 2. So in particular, it follows that V is not isomorphic to W. Well, and since 1 to the power 2 plus 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 2 to the power 2 plus 2 to the power 2 plus 2 to the power 2 is 16, the above simple modules are all simple d2 times 8 modules. So we have 5 modules coming from d2 times 4, and we just constructed 2 new simple modules. And it is easy to check now, since we have the explicit matrices, that the characters of both V and W are real valued. So in particular, the character table of D2 times 4 has only real numbers. But we have seen that the character table of SD16 has non-real values. So the character tables of these two groups are essentially different. Consequence, these two groups are not isomorphic. And this completes problem 2. Problem 3. Find the multiplicities of all simples SD16 modules in the SD16 module V5 tensor V6. So we use the notation as in problem 1. Recall that from the general theory, the multiplicity of a simple module in any module is just given by the inner product of characters. In problem 1, we computed explicitly the character table for SD16. So if you want to compute the inner product of characters, it's also very good to remember the cardinalities of the conjugacy classes. And we had an explicit list of conjugacy classes, so we have the cardinalities 1, 2, 2, 2, 1, 4, 4 of the conjugacy classes C1, C2, and so on. So let us start by computing the character of our module V5 tensor V6. So we have the character of V5, we have the character of V6. The character of the tensor product, we just take the product of the characters of the factors, just as functions. So in particular, we see that the outcome is 4, 0, 0, 0, minus 4, 0, 0. So now we should take the characters of all our simple modules, they are given by the character table, and take the inner product of each of these simple characters with this character 4000 minus 400. So for the module V1, so here is a very explicit computation. So we take 1 divided by the cardinality of G, and then we take the cardinality of the conjugacy class times the product of the character of the first module and the character of the second module conjugated. And similarly over all conjugacy classes. There are many zeros in the second character, so many things will just disappear. But at the end, we will have 4 coming from this 4 and minus 4 coming from here. And this gives us 0. So V1 doesn't appear in W. Similarly, we can compute the scalar product of the character of W with the character of V2. And we again will get 4 minus 4, which gives us 0. And the same thing happens with V3 and V4. So now V5 is a two-dimensional module, so we will have higher numbers. We will have 8 in the first place and minus 8 in the second place. But still 8 minus 8 will give us 0. But then interesting things happened with V6. So if you look at the character of V6, this is a character which has value negative of 2 on the conjugacy class C5. So in our formula, we will get here plus 8. So 8 plus 8 divided by 16 is equal to 1. So V6 appears with multiplicity 1 in W. And similarly, V7 appears with multiplicity 1 in W. So we also know that the characters of V6 and V7 are not real valued. So when computing the inner product, we need to take the complex conjugate of the entry which we have here. But since the value of the character of V5 tensor V6 at these conjugacy classes is still 0, so it doesn't matter. The summand which we'll get here will be still 0. But the answer to the problem is that the tensor product of V5 and V6 is isomorphic to the direct sum of V6 and V7. Problem 4. Prove that for any subgroup H of any group G, the induction from H to G of the regular H module gives us the regular G module. Let us denote by M the index of H in G. So this is the cardinality of G divided by the cardinality of H. And to start with, let us fix representatives G1, G2, and so on Gm in the cosets GH, where G is in G. Then every element in G can be uniquely written as a product of one of our representatives times an element in the subgroup. So any G can be written as G with the index I of G, this is an element from 1 to m, times the element H sub G in H. Let us compare the dimensions of the two modules on the two sides of the formula which we want to prove. The dimension of the regular G module is the cardinality of G. The dimension of the regular H module is the cardinality of H. The dimension of the induced module is equal the dimension of the module we start with times the index of the subgroup. This is equal to the cardinality of H times the cardinality of G divided by the cardinality of H, which gives us the cardinality of G. So the dimensions on the both sides of our formula, they do agree. To complete the proof of the problem, we prove the following claim, that sending an element G in the regular G module, so this is one of the basis elements, to the element G with the index I of G times H of G, and this is an element of the induced module, gives rise to an isomorphism of G modules. So we denote this isomorphism by phi. So as a linear map, phi is defined on the basis. Defining a linear map on the basis uniquely gives us a linear map. And by definition, phi sends a basis of the regular G module to a basis of the induced module, so it's an isomorphism of vector spaces. So what we really need to check is that this map is a homomorphism of G modules. So for two elements A and G in the group G, we know that the image of the product AG under phi, by definition, is the element G with a subindex I of AG times H of AG. Also, if we apply A to phi of G, this is equal to A times G with the index I of G times H sub G. And now we rewrite this as G with the index I of AG I of G times H, AG I of G times H sub G. But due to the uniqueness of the decomposition for the element AG, we have that G with the index I of AG should be equal to G with the index I of AG with index I of G, and the element H with the index AG should be equal to the product of H with the index A, G I of G, and H of G. And this completes the proof of the claim and our problem. Problem 5. Let G be the symmetric group S3 and H be its subgroup consisting of the identity and the transposition of 1 and 3. For any simple H module V, determine the decomposition of the induced module, induction from H to G of V, into a direct sum of simple G modules. So our subgroup H is very easy. It has two elements. So we know that this is a cyclic group of order 2. It has two modules. It has a trivial module. Both elements of the subgroup act as 1. It has dimension 1. And also we have the one-dimensional sign module. So here the non-identity element, the transposition of 1 and 3, acts as -1. We have also seen all simple S3 modules. We have the trivial S3 module, C-triv. We have the sign S3 module, C-sign. And we have the two-dimensional simple module, curly S, with the upper index 2, 1. And this is the complement of the trivial summand inside the natural module. We want to understand the multiplicities of all simples in the induced modules. By Frobenius reciprocity, the multiplicity of a simple W in the induction from H to G of V equals the multiplicity of V in the restriction from G to H of W. So the question is, how do simple S3 modules restrict to H? Of course, the trivial module restricts as a trivial module, and the sine module restricts as a sine module. So this is because the transposition 1, 3 is an odd element in S3, so it acts as -1 on the S3 sine module. So this restriction gives us the sine module for H. And then the matrix of the action of the transposition 1, 3 on the two-dimensional simple curly S with the upper index 2, 1, computed in the basis 1 minus 2 and 2 minus 3 of the natural module, is given by the matrix 0 minus 1 minus 1 0. So if you swap 1 and 3, then 1 minus 2 goes to 3 minus 2, which is minus the second basis vector, and 2 minus 3 goes to 2 minus 1, which is minus the first basis vector. And this matrix has different eigenvalues because it's not a scalar matrix. So it must have eigenvalues 1 and -1, which means that the restriction from G to H of curly S 2, 1 is isomorphic to the direct sum of the trivial H module and the sine H module. And turning the things around using the Frobenius reciprocity, we get the following answer, that the induction from H to G of the trivial H module is isomorphic to the trivial S3 module plus the simple module curly S 2, 1. So this is because the trivial H module appears in the restriction of the trivial S3 module and in the restriction of S 2, 1. Similarly, the induction from H to G of the sine H module is isomorphic to the sine S3 module plus S 2, 1. So this completes problem 5. Problem 6. Let G be a finite abelian group and H a subgroup of G. Prove that for any simple H module V, there exists exactly the index of H in G, simple G modules W, which restrict to V. In order to solve this problem, let us recall that any simple module over an abelian group has dimension 1, and that the number of pairwise non-isomorphic simple modules over an abelian group is equal to the cardinality of this group. So let V be a simple H module and W be a simple G module. Since W has dimension 1, its restriction to H must be simple. So by Frobenius reciprocity, this restriction is isomorphic to V if and only if W is a summand of the induced module induction from H to G of V. Note that this induced module has dimension the index of H in G. So therefore, it is isomorphic to a direct sum of exactly the index of H in G simple modules. Let us note that all these simple direct summands are pairwise non-isomorphic. Indeed, if we assume that some summand appears with multiplicity at least 2, then, by the Frobenius reciprocity, the restriction of the summand to H should have V with multiplicity at least 2. But this restriction has dimension 1, so it cannot have multiplicity 2 at all. So this is a contradiction. So therefore, all these summands are pairwise non-isomorphic, which means exactly that there are the index of H in G, different simple G modules which restrict to V. And this solves our problem. And the last problem 7, let G be a non-trivial group and let little g be a non-identity element in this group. Prove that there is a non-trivial simple G module V such that the evaluation of the character of V at our element G is non-zero. So let us note that if we consider the trivial G module, then the evaluation of the character of the trivial G module at any element of the group is equal to 1. So let us assume, towards a contradiction, that chi V of G is equal to 0 for any non-trivial simple G module V. Consider the regular G module C of G. So we know that the regular G module decomposes as the trivial G module with multiplicity 1 plus the direct sum of all non-trivial simple G modules V, which appear with multiplicity the dimension of V. Therefore, if we compute the value of the character of the regular G module at G, it will be equal to 1. So because we have the value 1 coming from the trivial module, and we have 0 coming from all other non-trivial modules V by our assumption. However, we know that the character of the regular module evaluated at any non-identity element is equal to 0. And this gives us our contradiction, which completes the proof. Let us finish with some extra problems and questions. Question 1. Determine the character table of the dihedral group D2 times 5. Question 2. Let G be a group and H a subgroup. Let V be a simple H module. Show that there exists a simple G module W such that V is a summand of the restriction from G to H of W. Question 3. Let G be a group such that it has an abelian subgroup H of index K. Prove that each simple G module has dimension at most K. Question 4. For any n, compute the character of the Sn module given by the tensor product of the sign Sn module with a simple module curly S with the upper index n-1, 1. And finally, question 5. Find the multiplicities of all simple D2 times 8 modules in the D2 times 8 module given by the tensor product of V with itself and then with W. And we use a notation as in the problem 2 in the lecture. Thank you very much and see you next time.